Okay, so in this video I'm going to do a momentum conservation problem. So we're going to be looking at flow between coaxial cylinders. So you can just imagine that there's a fluid in between the inside cylinder and the outside cylinder, and then as we rotate both of the cylinders, that's going to create bulk flow motion inside of the cylinders, or inside of the outside cylinder and outside of the inside cylinder in that annulus space. So if we look at the problem statement, we're told that it's an incompressible fluid. So I just like to write out all assumptions. So incompressible, constant temperature, so it's an isothermal system, constant temperature. The inside radius, so from here to here, is equal to Kr, some proportionality constant times the outside radius, which is just R. And then we're told the angular velocity of the inside cylinder, so that rotation is omega sub I, and the angular velocity of the outside cylinder is omega sub naught, or omega naught. So what I like to do when I'm solving momentum conservation equations is to first off write out all the assumptions that I'm making. So it's an incompressible fluid, it's isothermal, and then I like to determine what my driving force is. So the driving force for this problem is shear. So the momentum is going to be created by rotating these cylinders. So that's the driving force. Next, I like to just kind of inspect the problem and see if I can eliminate any of the velocity components. Excuse me. So just by inspection, we can see that we're definitely going to expect velocity in the theta direction created by the shear, created by the rotation of the cylinders. So we will expect a v theta. I can't foresee any kind of mechanism that would cause velocity to go from this inside to the outside here. So we're not going to have velocity in the r direction. Likewise, we're not going to have velocity in the z direction, because we're just assuming that all of these are laminar, rectilinear flow, so you're not going to have any kind of turbulence effects that are going to create these vertices that you get motion in all directions. So we're just going to assume that we only have flow in the theta direction. So all of that is to say that VR is equal to VZ is equal to 0. So the next thing that I want to do is just look at a continuity expression. So continuity, and forgive my terrible spelling, but that's supposed to say continuity. And just give me 1 second, I'll copy and paste the continuity expression for cylindrical coordinates. Okay, so here is the continuity expression for cylindrical coordinates. So I don't see expressly stated in the problem statement, but I'm going to assume that it's a steady state problem. So steady state. So we're going to get rid of the t dependence. So it's all incompressible, so we can factor out the density in all of these expressions here. We're told, or by inspection, we derive that VR and VZ are going to be 0, so those will cancel out. And then what we're left with is this 1 over r is equal to 0, so you can cancel out that 1 over r. And the simplified continuity expression for this problem would be the partial with respect to theta of v theta is equal to 0. So if I integrate the left-hand side and the right-hand side, what I end up with is that v theta is equal to a function of, so it's going to be a constant if you integrate the right-hand side, but it's a constant with respect to theta, so you could still have r and z dependence. So again, just kind of looking at this problem by inspection, we can see that we shouldn't expect any z dependence, but I would expect r dependence, because the angular velocity is going to be greater for the outside shell, or I should say the tangential velocity is going to be greater for the outside shell than for the inside shell. And so in order for mass flux to be constant, you would expect the velocity to change as a function of your radial position. So I'm going to say by inspection that v theta is equal to a function of r. Alright, so after you do the continuity expression, the next step is just to apply the momentum balance, or Navier-Stokes. So what I like to do is look at my boundary conditions before I pull up the Navier-Stokes equations, and that way the boundary conditions kind of inform you as to whether you should use the shear stress form of the Navier-Stokes equations, or if you should use the velocity simplification. So our boundary conditions are just two no-slip boundary conditions. So the theta velocity at radius r is going to equal to omega naught, so outside angular velocity, times the radius. And likewise for the inside at kr, we're going to have omega I times the radius again. So those are boundary conditions. So there's no shear stress involved in the boundary conditions, so we can use the simplified velocity version of the Navier-Stokes equation. And let me just go ahead and copy and paste that over here as well. Okay, so here's the momentum balance. And again, we're steady state, so we know that there's not going to be any time dependence, so we can cross that term off. V theta is equal to 0, Vz is equal to 0, V theta is equal to 0. So the V theta with respect to r term here, let's see, so V theta is a function of r, and then we have Vr, which is 0. So everything on the left-hand side is going to cancel out. I think I didn't explain it properly. Let's see. So time dependence gets rid of this transient term. So we have v theta with respect to r, but Vr is equal to 0, so that gets rid of that term. V theta with respect to theta. So theta is only a function, or v theta is only a function of r. So it's not going to depend on theta, so we can cancel that term out. Vz is 0, and Vr, so this is Vr, V theta, so Vr is 0. So everything on the left-hand side cancels out. Our driving force is not pressure, it is shear, so that's going to cancel out. Likewise, for the same reason, we don't have gravity as our driving force, or hydraulic pressure as our driving force, so we can get rid of the gravity term. Let's see, so V theta is not a function of theta, so we can get rid of this term. V theta is not a function of z, and Vr is 0. So the only term that we have left is just this partial with respect to r of 1 over r, partial with respect to r v theta term. So we have 0 is equal to some constant times this derivative, so I can just cancel out that constant. It's not going to play a role. So the simplified Navier-Stokes equation for this problem is the partial with respect to r of 1 over r, partial with respect to r again, times r v theta, and that is equal to 0. So if I integrate both sides, let me just go ahead and scroll down 1 second. Okay, so if I integrate both sides, I get a 1 over r times some arbitrary constant. I'm going to multiply the 1 over r over to the right hand side, and then I end up with this expression here after integrating and multiplying by r to both sides. So I have the partial with respect to r of r v theta is equal to c1 times r. and I'm going to call it C1 tilde actually, and you'll see why I did that in a second here. But then I'm just going to integrate once more both sides, and I get r v theta is equal to C1 tilde r squared over 2 plus a C2 term. And then if I divide by r to both sides, I get a v theta is equal to a C1 tilde r over 2 plus C2 over r. So because this is an arbitrary constant, what I can do is I can absorb this 2 into this arbitrary constant and then just give this arbitrary constant a different name. So I'm going to say that V0 is equal to C1R plus C2 over R. And that's just going to simplify the algebra that I'm going to have to do in the next step. So let me go ahead and rewrite the boundary conditions. So the boundary conditions were that the velocity in the theta direction when r is equal to the outside radius is equal to omega naught r, and likewise for the inside radius we have this omega I times kr. So I'm going to plug those boundary conditions into this problem right here, and what I get is that I'll do it over here. So v theta of r gives me a C1 r plus C2 over capital R, and that is going to equal to an omega naught r. And likewise, v theta of kr is equal to C1 times kr plus C2 over kr equal to omega sub I kr. Alright, and what I'm going to do is I'm going to divide all of these terms. So if I divide all of these terms by r, I get a C1 plus C2 on r squared equal to omega naught. And then I can also do the same thing and divide everything in this bottom equation by kr, and I get C1 plus C2 on kr is equal to omega sub I, and that's kr squared on the bottom here. So the reason why I did this simplification is that I recently just learned a new method for solving systems of equations, and it's a little bit wacky, I guess. I don't know. You don't have to solve it this way, but I learned a new method and I'm going to play around with it. It's called Cramers Rule, and it involves taking the determinants, and I'll go ahead and walk you through that in 1 second here. Okay, so with Cramers Rule, say I want to solve this system of equations right here, where I have ax plus by equals c, a tilde x plus b tilde y equals c tilde. So what I can do to solve for x is I can say that x is equal to, and then I'm going to take the determinant of all of these coefficients out front on the denominator. So I'm going to go a, b, a tilde, b tilde. So I'm going to take the determinant of that in the bottom, and then in my x column of this determinant matrix, I'm going to put the solution side. So that would be c tilde. And then I'm just going to copy whatever's in the denominator for the y column. So I get a b and a b tilde. And then likewise, when I'm solving for y, the denominator is going to be the same as it is in the x case. So I'm going to have a, b, a tilde, b tilde. And then I'm going to put the solutions, c and c tilde, in the y column. So c tilde, and then I just copy whatever's in the denominator for the x column, a tilde. So applying that same concept, I'm going to use these two equations to determine c1 and c2. So c1 is my x in this case, and c2 is my y in this case. So c1 is equal to, so I'm going to have a 1 and a 1 over r squared, and then another 1 and a 1 over kr quantity squared. So I'll take the determinant of that in the denominator, and then for the numerator I'm going to put the solutions in the x column because C1 is x in this case. So we'll have omega naught and omega sub I, and then for the right hand column I'm just going to copy whatever's in the denominator, so 1 over r squared and 1 over kr quantity squared. And then I'm going to take the determinant of the numerator and the denominator, so I'll get a sigma naught over kr quantity squared minus a sigma sub I over an r squared, and I'm going to divide that by a 1 over kr quantity squared minus a 1 over r squared. So I'm just going to remind you again that this is just a new method for solving the system of equations that I recently discovered, but you can just do elimination or substitution and you'll end up with the same answer. So you don't have to do this if you don't know how to take a determinant. But if I simplify this expression, what I end up with is that C1 is equal to omega naught minus omega sub I k squared. So I'm just multiplying this term by k squared, and then I have a kr squared that I bring down to the denominator, and then again I'm multiplying this term by k squared, and then I brought down that kr in the denominator, and then I multiply each of those, and then that gives me try that again, 1 minus k squared in the denominator. And then C2, so my denominator is going to be the same, 1 over r squared, 1 over quantity of k r squared, and then I get a 1 1, so I just take whatever's in the denominator for the x column, and then I put the solutions in the y column because C2 is represented by y in this equation, this example over here. So I'm going to get my sigma sub I, or sigma sub naught, sorry, because that is this value right here, and sigma sub I here. So then I'll get a sigma I minus sigma naught over the same denominator here. So it'll be a 1 over kr squared, quantity squared, minus 1 over r squared. Okay, and if you simplify this one, you'll get k squared r squared times sigma sub I minus sigma naught over 1 minus k squared. Okay, so what you want to do now is go ahead and plug these constants that you solved for into your V naught of our expression up here. So let me go ahead and scroll down a little bit and create some room. Okay, so we had that V theta of R is equal to C1R plus C2 on R. So now I'm going to plug in the constants that we solved for. So V theta of R is equal to, so I get a 1 over 1 minus k squared. I'm going to multiply that by the quantity of, so I'm plugging in C1 here. So I pulled out the 1 minus k squared from both of our constants. So now in the numerator of C1 I have a sigma naught, or and sigma sub I k squared, and then I'm multiplying that by r. Then I'm adding C2, so I pulled the denominator out already, so I'm just interested in the numerator. So I have a k squared r squared times sigma sub I minus sigma naught over r. Okay, and if I pull out a factor of kr, so if I divide everything inside of the parentheses by kr, and then I multiply the numerator of this outside by kr, then I end up with this final answer here, kr over 1 minus k squared times the quantity of sigma naught. Try that again. So sigma naught minus sigma sub I k squared then an r over a kr term here. Then I'm going to add to that a sigma sub I minus sigma naught times the quantity of kr over r. So that is my v theta of r. And if I scroll up, you'll see that that is the expression that we were asked to derive. So that's this right here. So that is the velocity distribution in the fluid. So next it asks to solve for the torque to maintain the motion. So let me go ahead and scroll down, get some free space here. Okay, so we're solving for torque. I couldn't find a very good analytical expression for torque. So this is my kind of definition of what torque is. So it is the integral over the area of the shear stress of the fluid, shear stress evaluated at, so it's tangential shear stress, so tangential, but you want to evaluate it at some tangential length. So in this case, we're looking at a cylinder. Let me scroll up to the picture 1 second. So we're looking at a cylinder, and then we're asked to find the torque for the outside cylinder and for the inside cylinder. So the tangential direction in this case of the outside cylinder is going to be into the fluid, and so it's going to be in the radial direction. So scroll down again. So evaluated at some tangential length will be we'll evaluate the radius at the outside cylinder and the radius at the inside cylinder. But anyways, the torque is going to equal to the shear stress multiplied, the shear stress evaluated tangentially to whatever surface you're interested in, and then you're going to multiply that by a lever arm. So that's the length that the shear stress is operating over, and you're going to multiply that by a Jacobian, and then your differential area unit. Okay, and if you don't remember the Jacobian for cylindrical coordinates, so for cylindrical, the Jacobian is going to just be r, and then for spherical, would be, so it depends on what you're referring to, your radius in spherical. In a lot of math books, it'll be rho squared sine phi. It could be r squared sine phi, but basically it's the radius of the sphere times the sine of, so it should be your phi angle actually, so sine phi. May actually retract that, it is theta, so it's rho squared sine theta. And then for Cartesian coordinates, it's just 1. And then your dA for Cartesian would be like dx, dy. Cylinder would be dr, d theta. Spherical would be d rho, d theta, d phi. So that is kind of my general torque calculation. But if we look specifically at this problem, we're interested in the torque of the inside and outside shell. So torque outside shell is going to equal to the integral from 0 to L, where L is the height of the cylinders, and the integral from 0 to 2 pi, 1 revolution around the cylinder. And then from the outside, let me just draw another cylinder here. And then we add a smaller cylinder on the inside. Okay, so from the outside, you have to go inward in the negative R direction for you to create shear stress acting on the fluid. So it's going to be a negative shear stress here. So you get a negative tau. So theta momentum in the R direction. And then you're going to evaluate that in the tangential direction. So that'd be for R, and you're going to evaluate it at the outside radius, so R equal to capital R. And then the lever arm is going to be the outside radius as well. And then the Jacobian, so the Jacobian for cylindrical coordinates is R, and then we're evaluating R at the outside radius, so this would give us an R squared. So you get an R from the lever arm and R from the Jacobian, and then I get a d theta dz here. And then let me go ahead and copy and paste the expression for the Newtonian viscosity for the shear stress. 1 second. Okay, so here is the expression for the shear stress. So if we kind of inspect it, we know that v theta is a function of r, so this term is going to survive, but Vr was determined to be 0 in the initial problem. So the only thing that survives is this left-hand term here. So if I'm interested in evaluating that at r equals to r, so you can imagine that there's a capital R dependence in there. Or rather than do that, let me just go ahead and let's just look at this shear stress term. So tau of theta r evaluated at r equal to r is a negative mu times an r partial with respect to r of our b theta term up here. Just scrolling up 1 second. So b theta is up here, and then it's going to be b theta over r. So if I divide our b theta expression by r, I can see that this term is going to drop out, and all I'm going to have left is an r squared term on the denominator of the second term right here. So I'm going to have a k r over a 1 minus k squared times the quantity of theta I minus, or it's sigma, and then I have a kr over an r squared term here. So if I take the derivative of this inside function, what I end up with is a negative 2 from this term right here, mu r, and before I forget, we need to evaluate this at r equal to capital R. So negative 2 mu r, that's right here, and then I multiply that by kr over 1 minus k squared. times the quantity of sigma sub I minus sigma naught. And then I get a kr over r to the third. Okay, I'm evaluating all of that at r is equal to r. So I'm scrolling down 1 second. Okay, so I'm evaluating this expression with r. So if I plug in a capital R here, I have an R, an R, and an R. So I have 3 R's. All those R's are going to cancel out. And then I'll end up with this right here. So negative 2 times mu, and then I had k squared over a 1 minus k squared, and I'm going to multiply that by sigma I minus sigma naught. So that is my shear stress term evaluated at r equal to capital R. So I'm integrating over theta and z. So when I integrate this expression over theta, I get a theta here, and then I evaluate it from 2 pi to 0. That gives me a factor of 2 pi in my final answer. Likewise, I get a z, and if I evaluate that from L to 0, I get an L term. So my final answer is going to look like negative 4. So I'm multiplying the 2 pi by this 2 here too. So I get a negative 4 pi times a mu, and then I have this r squared term here, k and r squared at a k squared down here. I'm going to divide that by a 1 minus k squared and multiply by r sigma sub I minus sigma sub naught. And I forgot to multiply by r length, which I get from this integral again. So that is the shear stress for the outside shell. So the shear stress for the inside shell, I'll set up the integral, and then I'm not going to evaluate it because it's basically the same concept as the outside shell. But it's the double integral over the area, so 0 to L, 0 to 2 pi of the shear stress so it's theta momentum in the r direction, and it's positive this time because the rotation of the inside cylinder is going to cause fluid motion in the positive r direction. Hopefully that makes sense. And then we're going to evaluate it at the tangential length kr, and then I'm going to multiply it by the lever arm kr, and I'm going to evaluate it over the Jacobian evaluated at the length kr. So I guess let me formalize it. So the Jacobian evaluated at r equal to kr, and then that would be d theta dz. So in the last problem I had the Jacobian r evaluated at lowercase r equal to capital R. So in this case it is r equal to this proportionality constant times the capital R. So if you evaluate this expression, you'll end up with this exact same thing except for positive. So it's the negative of t of the outside. Alright, so that is momentum conservation on coaxial rotating cylinders.